The sky above the Sun was unusually active on this day, November 10th, 2025, when 3i Atlas registered a series of anomalies that defied its established detection patterns. The observatory's instruments, finely tuned to capture faint solar proximal phenomena, recorded an object, or perhaps a complex set of phenomena, approaching the solar corona at a velocity inconsistent with known solar system bodies. Its path did not match any predicted orbit, and its signature across multiple spectrums was irregular. Infrared sensors picked up faint but distinct thermal variations, while ultraviolet and X-ray instruments indicated an energy output that fluctuated in ways not typically associated with comets or solar ejecta. The first confirmation came almost immediately from 3i Atlas redundant sensors. While single instrument readings can often be anomalies, false positives caused by cosmic rays, sensor errors, or electronic noise, here the anomaly persisted across independent channels. It was small, yet bright enough to cast a measurable perturbation in the surrounding solar plasma. This was no routine flare or fragment. It moved against the expected flows, its trajectory seemingly aware of solar magnetic fields, responding with subtle but precise deviations. As the data streamed in, analysts noted the velocity profile. Too rapid for typical coronal mass ejections, too consistent to be random debris. Early calculations suggested an object moving at a fraction of the solar escape velocity, yet its approach angle was unusual, neither aligned with the ecliptic plane nor with known asteroid belts. Moreover, the spectral analysis revealed absorption lines inconsistent with standard solar matter, hinting at a composition that was either highly reflective, unusual in density, or partially composed of unknown elements. Observers had been monitoring the Sun constantly for decades, cataloguing every flare, filament and sunspot. Yet even within this extensive database, nothing matched the readings of the past 24 hours. Some early comparisons suggested parallels to the brief anomalies recorded by 3i Atlas in mid-2024, events that at the time were dismissed as sensor noise. This time, however, the anomaly persisted long enough and across enough instruments to force analysts to reconsider earlier assumptions. The implications were immediate. If the object was natural, it represented a solar proximal body unlike any documented. If it was artificial, intentionally or otherwise, it raised questions about technology and physics that extended beyond current human understanding. By the late hours of November 10th, researchers were not only confirming the anomaly, but beginning to cross-reference global datasets, seeking corroboration from other observatories and space-based solar instruments. Yet even in this flurry of verification, the anomaly retained an enigmatic quality. Its exact size was difficult to determine. Initial estimates suggested something on the scale of tens of meters, but the irregular reflections and emissions made precise calculation nearly impossible. The object did not appear to be shedding detectable fragments, nor did it display characteristics of known comets or asteroids entering the inner solar system. As the Sun dipped toward its standard horizon, in observational terms, the anomaly remained, defying conventional categorization. And as one possibility faded, another emerged. Perhaps this was a manifestation of a solar phenomenon not yet understood, a structure formed within the corona itself, behaving almost like a particle with agency, interacting with electromagnetic fields in unexpected ways. By nightfall, the team had reached a cautious consensus. The observation could not be ignored. It demanded continuous monitoring, detailed spectrographic analysis, and a re-evaluation of previous anomalies in the context of this new data. Yet the central question persisted. What exactly had 3i Atlas encountered? Its trajectory, energy signature, and apparent composition challenged every model currently used to predict solar proximal objects, and so the observation entered the record not merely as a dataset, but as a developing event, a live puzzle unfolding at the heart of the solar system. With instruments continuing to track its every movement, researchers knew the story had only begun. But this was only the first moment in a chain of observations that would push understanding further than ever before. What had started as an unusual blip in 3i Atlas's sensors was quickly becoming a defining event, one that demanded a full investigation into its characteristics, trajectory, and potential origin. Each new reading added complexity, revealing that the object, or phenomenon, was more than a simple solar anomaly. Its behavior, both predictable in part and baffling in other ways, suggested a new category of solar proximal activity, one that would dominate the next series of analyses and challenge long-held assumptions about the immediate solar environment. 3I Atlas's initial detection logs provided an extraordinary level of detail, far beyond what would normally accompany a routine solar observation. Every photometric and spectroscopic reading was catalogued in real time, and it quickly became clear that the anomaly exhibited characteristics unlike anything previously recorded. Across the visible spectrum, the object presented a dim, diffuse glow, yet in infrared it became significantly more pronounced, suggesting an absorption and re-emission profile that defied typical solar proximal bodies. Its brightness was inconsistent, fluctuating subtly yet measurably over periods as short as 30 seconds. Analysts first attempted to reconcile these fluctuations with natural phenomena. Solar flares and coronal mass ejections often produce irregular light curves, but they follow predictable energy release patterns and have characteristic velocities. The anomaly, however, displayed a consistency in its movement and spectral behaviour that seemed deliberate, almost controlled. By plotting its path against known coronal currents, magnetic loops, and the solar wind, it was evident that it did not passively drift with the plasma. Instead, it appeared to respond to the environment, navigating through magnetic turbulence with a precision that, if natural, suggested a heretofore unknown physical mechanism. Data from the ultraviolet spectrum provided further intrigue. The anomaly emitted faint lines corresponding to ionized metals, yet these emissions were intermittent, shifting subtly in wavelength as the object approached perihelion near the solar surface. Some of the emission lines corresponded to elements rarely observed in the solar corona, raising questions about the anomaly's composition. Was this an asteroid with a highly unusual mineral content, or a manifestation of a solar phenomenon that synthesized transient elements under extreme energy conditions? Either scenario required a reconsideration of existing models. The X-ray detectors aboard 3I Atlas revealed another anomaly, brief, almost pulse-like bursts of energy that occurred in perfect synchronization with its observed trajectory changes. While the amplitude of these pulses was minor compared to a typical flare, their periodicity was precise. Analysts noted that no known natural body could generate such finely tuned bursts while moving through the highly turbulent solar corona. Furthermore, 3I Atlas's motion sensors tracked the anomaly at multiple points along its trajectory, showing accelerations inconsistent with standard orbital mechanics. The object's speed fluctuated by several kilometers per second, but these changes were not random. Instead, they occurred in coordination with nearby magnetic flux variations. Early computational models suggested that if these movements were driven purely by electromagnetic interaction, the object would require an extremely high conductivity and a shape optimized to exploit Lorentz forces, adding another layer of complexity. Simultaneously, radar cross-sections derived from Doppler analysis suggested a compact form factor with high reflectivity, yet optical and infrared imagery implied a partially diffuse structure. This contradiction prompted speculation that the object might possess a heterogeneous composition, dense cores embedded within a less dense envelope, or even a semi-transient structure sustained by high-energy plasma or magnetic confinement. Every reading forced the team to cross-reference against prior detections. Historical anomalies in solar proximal space were rare, but 3I Atlas had catalogued at least 5 similar but less pronounced events over the past 2 years. In each case, the objects were fleeting, their properties only partially recorded before dispersing into the solar wind. This time, however, the anomaly persisted for over 12 hours, providing an unprecedented opportunity to track and analyze its behavior comprehensively. Observers began overlaying the object's trajectory onto a 3-dimensional model of the inner solar system, factoring in gravitational perturbations from the Sun, Mercury, and Venus. Even with these adjustments, the object's path remained irregular. At times, it appeared to accelerate slightly against the expected vector, then drift in alignment with the solar equatorial plane before sharply deviating again. This suggested that either an unknown force was acting upon it, or it possessed an intrinsic propulsion or guidance mechanism, a possibility that would become a focal point of intense debate in the following days. The anomalies were not limited to motion and energy emissions. Spectropolarimetric readings indicated subtle changes in the polarization of reflected light. These shifts correlated with the anomaly's position relative to solar magnetic loops, implying an interaction between the object's surface, or envelope, and the local electromagnetic field. While the effect was small, it was consistently measurable, hinting at a structural or material property that allowed the anomaly to manipulate or respond to magnetic flux in ways not documented in natural solar system bodies. As data continued to pour in, analysts faced the challenge of integrating multiple datasets with varying resolutions and sampling rates. High-resolution infrared imaging suggested a lobed structure, possibly rotating or oscillating, while ultraviolet readings implied localized energy emissions from specific regions. Radar and photometric data, when overlaid, suggested a combination of reflective and absorptive surfaces, producing an irregular, almost chimeric observational profile. By the end of the first observation cycle, it was clear that the detection could not be classified using standard nomenclature. The combination of persistent trajectory, irregular acceleration, spectral anomalies, and electromagnetic interaction suggested a category of solar proximal phenomena that had not been defined. Researchers began the meticulous process of segmenting the data into discrete observational windows, each analysed for consistency, deviation, and correlation with solar activity. And yet, despite this exhaustive initial assessment, one question loomed above all others. What fundamental physics could explain these behaviours? Each hypothesis required stretching conventional understanding, whether proposing an unusual natural object with extreme electromagnetic properties, a transient solar plasma structure exhibiting quasi-stable coherence, or an artificial object capable of navigating near the Sun. As the anomaly continued its approach, analysts prepared to examine it under increasingly precise spectroscopic methods, hoping to reveal finer details of composition and structure. But even with these advanced techniques, the observation remained incomplete. The deeper they probed, the more complex the picture became, raising new questions even as old ones were answered. And so the stage was set for the next phase of investigation, understanding the context of this detection relative to historical anomalies, patterns in solar proximal activity, and prior 3I Atlas observations. Each detail, however minute, could unlock insight into the true nature of this persistent, enigmatic presence near our star. The anomaly detected by 3I Atlas did not exist in isolation. Historical records reveal a pattern of fleeting, poorly understood objects passing near the Sun, though none had persisted long enough or been observed with sufficient precision to allow rigorous analysis. Over the past 3 decades, solar observation missions from both ground-based observatories and spaceborne platforms documented transient events often dismissed as instrumental noise, micrometeoroid impacts, or atypical solar ejections. When revisited in light of the current anomaly, these prior records acquire new significance. In 1998, the Solar and Heliospheric Observatory recorded an unusual brightening near the Sun's southern hemisphere. The object, only visible in extreme ultraviolet, appeared for less than 3 hours. Contemporary analysis categorized it as a coronal microflare, yet the trajectory inferred from the limited images did not align with typical solar plasma motion. While dismissed at the time, this incident shares characteristics with the current detection: brevity, unusual positioning relative to the ecliptic, and localized spectral anomalies. Further anomalies were recorded during the Parker Solar Probe's early missions. In 2021, a transient object was captured within the inner corona, exhibiting irregular motion and a faint fluctuating thermal signature. Unlike typical cometary fragments, its path did not conform to gravitational predictions, and it seemed to avoid direct interaction with dense solar plasma streams. However, the instruments then lacked the spatial resolution and multispectral integration capabilities of 3I Atlas, leaving much of its nature speculative. In each historical case, the anomalies were isolated events. They lacked cross-sensor verification and often appeared in datasets that were partially corrupted or incomplete. Analysts of the past generally assumed natural explanations: highly eccentric asteroids, outgassing comet remnants, or temporary magnetic reconnections within the corona. Yet the anomalies shared subtle, unrecognized consistencies, precise but irregular movements, brief energy pulses across multiple wavelengths, and in some instances, hints of materials not commonly associated with known solar or planetary matter. The importance of the historical context lies not merely in cataloguing prior events, but in revealing a persistent pattern. solar proximal anomalies occasionally occur, often overlooked due to their transient nature. With 3 Ars Atlas's detection, the anomaly lasted over 12 hours, with continuous, high-resolution readings across spectrums. This duration allows a level of analysis unprecedented in historical records. In effect, past anomalies can now be re-examined under a new paradigm, considering not only their existence, but also the potential mechanisms capable of producing such behaviour consistently. Beyond isolated anomalies, broader solar activity patterns provide additional context. The Sun's magnetic field, measured over decades, has shown predictable oscillations, yet brief disruptions and localized deviations occur frequently. Some anomalies have coincided with peaks in magnetic flux, while others emerge during quieter periods. The 3 Atlas detection, occurring during moderate solar activity, aligns neither with major sunspot emergence nor with coronal mass ejections, further emphasizing its irregularity. Historical data also provide a framework for understanding observational biases. Until recently, solar observation technology was limited in temporal resolution and spectral diversity. Early instruments could capture only brief glimpses of anomalies, often missing transient signatures in ultraviolet X-ray or infrared ranges. Consequently, objects with brief lifespans or unusual spectral signatures went largely undocumented. The continuous multispectral monitoring capabilities of 3i Atlas now reveal that such phenomena may be more common than previously thought, though still rare enough to warrant intense scrutiny. Cross-referencing historical observations with modern detections also raises questions about categorization. Conventional solar science classifies objects based on orbit, composition, and interaction with solar plasma. Historical anomalies often defy these classifications, appearing to behave in ways that blur natural and artificial boundaries. For instance, early records suggest objects that resist expected gravitational influence, interact minimally with solar plasma despite close proximity, or exhibit energy emissions inconsistent with known materials. The 3i Atlas anomaly amplifies these inconsistencies, suggesting a continuum of phenomena previously unrecognized. The historical context highlights an important principle. Repeated observation, combined with improved instrumentation, transforms ambiguity into actionable data. Whereas past anomalies remained speculative, today's continuous readings allow scientists to identify patterns in trajectory, energy output, and spectral behavior. This approach frames the current anomaly not as an isolated curiosity, but as part of a broader, poorly understood solar proximal phenomenon. Additionally, historical analysis provides benchmarks for instrumentation accuracy. By comparing current readings with documented anomalies, analysts can calibrate expectations for thermal emissions, reflection properties, and energy fluxes. Deviations from these benchmarks, such as those seen in the 3i Atlas anomaly, become significant indicators of new physics or previously undetected object types. In other words, the anomaly's unusual behavior becomes more pronounced when viewed against a backdrop of decades of solar observation, reinforcing its uniqueness and challenging existing models. Yet the historical perspective also cautions against hasty conclusions. Some anomalies, once thought extraordinary, were later explained by calibration errors, cosmic ray interference, or even software glitches. This reinforces the need for meticulous verification. Every data point must be cross-referenced with multiple instruments, both on 3i Atlas and via external observatories, before firm interpretations can be drawn. By contextualizing the 3i Atlas detection within historical records, a pattern begins to emerge. Transient solar proximal anomalies occur sporadically, often overlooked, but occasionally persistent enough to allow detailed study. Each event challenges the limits of conventional understanding, highlighting gaps in models of solar proximal dynamics, material behavior under extreme conditions, and the interaction between small bodies and the Sun's magnetic and radiation fields. As we turn to the next stage of investigation, the historical record serves as both a caution and guide. It demonstrates the need for careful analysis while emphasizing the potential for discovery. Anomalies like the one now unfolding are rare, but not unprecedented. Each offers a window into processes or objects that defy conventional expectations, and together they form a tapestry of solar proximal phenomena that 3i Atlas is uniquely positioned to study. And so, the anomaly observed today sits within a lineage of unexplained events, some fleeting, some partially documented, all leaving questions that echo across decades of solar observation. Understanding its significance requires integrating this historical context with detailed instrument analysis, trajectory mapping, and energy profiling, setting the stage for a deeper examination of its physical characteristics and the mechanisms that govern its behavior. Before drawing conclusions about the anomaly, 3i Atlas's team devoted extensive effort to examining the instrumentation itself. When an observation challenges all known models, the first question must always be whether the instruments are performing as expected. A single sensor reading could be corrupted by cosmic rays, thermal drift, or software glitches. But in this case, the anomaly persisted across multiple independent systems, prompting a comprehensive instrumentation audit. The primary optical sensors were first scrutinized. These high-resolution cameras, calibrated daily against standard stars, had historically shown remarkable stability. Analysts reviewed calibration logs from the previous week and confirmed that no deviations could account for the observed fluctuations in brightness and trajectory. Even transient anomalies such as electronic noise spikes or cosmic ray interference could not replicate the object's behavior, which was consistent over 12 continuous hours. Next, spectrographs were examined. These instruments, sensitive to visible, ultraviolet, and infrared light, are particularly susceptible to minor misalignments. Small deviations in grating orientation or detector sensitivity could produce spurious absorption or emission lines. Every element, however, passed rigorous validation tests. Laboratory simulations demonstrated that no known instrument error could produce the specific pattern of shifting ultraviolet emission lines combined with infrared intensity modulation observed in the anomaly. Particle detectors added another layer of verification. These instruments monitor high-energy particles such as electrons, protons, and cosmic rays in the vicinity of the solar environment. Analysts compared the readings during the anomaly with background flux levels and prior observations. The detectors recorded consistent patterns of low-level particle interaction corresponding with the anomaly's movement, an indication that the readings were not artifacts of random solar particle events. Redundant verification came from independent timing and orientation systems. 3i Atlas uses multiple gyroscopes and atomic clocks to maintain precise pointing accuracy and time synchronization. Analysts confirmed that all systems reported concordant data. The recorded position of the anomaly at each timestamp matched across instruments within a margin of error of a few arc-seconds. Such precision ruled out misalignment or timing errors as potential explanations for the anomalous trajectory. Furthermore, the observatory cross-referenced its readings with external instruments, including spaceborne solar observatories and ground-based solar telescopes. While data from these sources had lower spatial resolution, several corroborated unusual energy emissions coinciding with the anomaly's passage. This external validation reduced the likelihood that the observations were limited to 3i Atlas's instrumentation, reinforcing the anomaly's legitimacy. Environmental factors within the observatory were also considered. Thermal expansion of instruments, electronic interference, and internal vibrations could theoretically affect readings. Environmental logs showed stable temperature and power conditions during the entire observation period. Vibration sensors indicated no anomalies, and electronics diagnostics confirmed consistent signal integrity. In short, nothing in the observatory's physical environment could have produced the observed effects. Software pipelines underwent detailed inspection. As well, data from 3i Atlas is processed in real time using algorithms that correct for atmospheric distortion, sensor drift, and known artifacts. Analysts simulated the exact processing steps with controlled datasets, ensuring that no artifact or bug could create false trajectories or spectral anomalies. Every test returned expected results, further confirming that the observed anomaly was not a byproduct of software processing. Additionally, redundancy built into the observatory's design offered another safeguard. Parallel sensor arrays, independent data channels, and separate recording systems all documented the anomaly consistently. The convergence of readings across independent systems dramatically reduces the probability of false detection, supporting the conclusion that the anomaly represents a real physical phenomenon near the Sun. Interestingly, the anomaly's detection also prompted a re-evaluation of historical instrumentation performance. Analysts revisited earlier anomalous events recorded by 3i Atlas and other solar observatories. In several cases, subtle instrument limitations may have contributed to uncertainty. leading to dismissal of potentially relevant anomalies. With the current detection, analysts could now apply refined cross-checking techniques retroactively, providing a more complete picture of prior events. After exhaustive analysis, the instrumentation check confirmed 3 critical points. First, the anomaly was not an artifact of 3 Atlas sensors or software. Second, corroboration from independent instruments supported the readings. Third, the anomaly's behaviour consistently exceeded known natural or instrumental explanations, establishing it as a genuine event requiring detailed physical and theoretical analysis. This verification phase was essential before advancing to the next stage, understanding the anomaly's physical characteristics. Knowing that the instruments were reliable allowed analysts to interpret spectral lines, thermal variations, and trajectory data with confidence. Only with this foundation could meaningful discussion of mass, composition, reflectivity, and potential interaction with solar forces begin. By ensuring that the instruments were functioning correctly and eliminating potential sources of error, the team laid the groundwork for a rigorous scientific investigation. The next phase would focus on translating these verified readings into insights about the anomaly's physical nature, a step that would challenge both conventional understanding and analytical ingenuity. And as one verification concluded, another question immediately emerged. If the instruments were accurate and the anomaly real, what could possess such unusual physical characteristics while moving near the Sun with such precision? The stage was set to explore the anomaly's composition, structure, and energy interactions, leading directly into a deeper understanding of its origin and behaviour. The physical characteristics of the anomaly revealed by 3I Atlas were unlike anything routinely observed in the inner solar system. By combining high-resolution imaging, spectral analysis, and electromagnetic readings, researchers began to build a profile of its size, structure, and composition, each observation deepening the puzzle. Initial imaging suggested a compact object with dimensions roughly estimated in the tens of meters range, though optical diffraction and infrared scattering complicated precise measurement. Its apparent shape was irregular, with lobes or protrusions visible in thermal imaging that did not correspond to any known asteroid morphology. Unlike typical comets or meteoroids, it displayed no visible outgassing or dust tail, even when passing within close proximity to the Sun's coronaspectral data offered the first clues to composition. Infrared readings indicated regions of high thermal emission alternating with cooler areas, implying heterogeneous surface properties. Some sections absorbed solar radiation efficiently, while others reflected it, creating the unusual light curve observed across multiple wavelengths. In the ultraviolet spectrum, intermittent emission lines suggested the presence of ionized metals uncommon in standard solar system bodies, including traces of elements that may be transient under extreme energy conditions. This raised questions about whether the anomaly was natural, a fragment of exotic material, or an unknown construct interacting with solar plasma reflectivity patterns added further complexity. Radar cross-section analysis indicated that parts of the object were highly reflective, while other regions absorbed or diffused electromagnetic waves. The combined data suggested a heterogeneous composition, dense, metallic cores embedded within lower density, possibly plasma-stabilized outer layers. This hybrid structure would be unique, suggesting either a rare natural process or an artificial origin capable of withstanding extreme thermal and radiative stress near the Sun. Rotation and motion analysis provided additional insight. Fluctuations in brightness and spectral signature implied slow rotation or oscillation of surface features, but not in a predictable, uniform manner. Some variations corresponded with local magnetic field orientations, hinting at interactions with the Sun's electromagnetic environment. The anomaly may have been exploiting magnetic forces to stabilize or guide its motion, a property unprecedented in known natural bodies. Thermal behavior was equally anomalous. Infrared measurements indicated that the object's surface temperature responded dynamically to solar proximity, yet in ways that did not align with simple radiative equilibrium models. Certain regions cooled faster than expected, while others retained heat disproportionately, creating a thermal mosaic inconsistent with standard asteroid or cometary physics. This suggested either a material with unusually high thermal conductivity differences or an active process regulating temperature, possibly a form of structural or plasma-induced stabilization. Further analysis focused on density and mass. By observing the anomaly's response to solar gravitational gradients and coronal plasma interactions, analysts inferred a relatively high density in the core, enough to maintain integrity under tidal forces close to the Sun. The outer envelope appeared less dense, possibly composed of ionized gases or plasma held in coherent form by magnetic fields. Such a layered configuration could explain the simultaneous absorption and reflection observed in multiple spectrums, as well as the minor but precise adjustments in trajectory detected by 3I Atlas. The object's surface properties also suggested unusual chemical or material interactions. Spectropolarimetry indicated variations in light polarization consistent with structured surfaces interacting with magnetic flux. These variations were subtle but reproducible, implying a surface capable of modifying or responding to the Sun's electromagnetic environment. No natural solar system body has been observed with this combination of density gradients, thermal behavior, and polarimetric response, emphasizing the anomaly's exceptional nature. Analysts then considered whether the anomaly's properties could result from a solar proximal plasma phenomenon rather than a solid object. Simulations suggested that a stable, quasi-coherent plasma formation could mimic the observed thermal and reflective properties under certain conditions, but such structures are typically transient, lasting only seconds or minutes. The anomaly's persistence over hours suggests either a new type of plasma stability or a hybrid structure combining solid material and magnetically confined plasma. Further comparisons with historical anomalies reinforced this uniqueness. Previous short-lived detections lacked sufficient multispectral data to resolve thermal heterogeneity or polarimetric interactions, leaving open the possibility that those events were early manifestations of the same type of phenomenon. The 3I Atlas detection, by contrast, offered unprecedented temporal continuity and spectral coverage, allowing researchers to document subtle variations in physical behavior over time. The physical profile raised immediate questions about survivability. Passing so close to the Sun exposes any body to intense radiation, high-energy particle bombardment, and extreme gravitational stress. For the anomaly to maintain its structural integrity, it must possess extraordinary thermal and mechanical resilience. This resilience, combined with its precise trajectory adjustments, implies either an exotic natural material or an active process governing movement and energy distribution. In conclusion, the anomaly's physical characteristics, size, shape, heterogeneous composition, thermal mosaic, polarimetric response, and structural stability defy straightforward classification. Each attribute challenges conventional understanding of solar proximal bodies, and together they form a coherent but perplexing profile that cannot be readily explained by standard astrophysical models. As the investigation proceeded, one pressing question emerged. How did these physical properties influence the anomaly's movement and interaction with the Sun's environment? Understanding this relationship would require detailed trajectory analysis, mapping orbital mechanics against solar forces, and quantifying the energy exchanges between the object and its surroundings. It is this intricate interplay between physical characteristics and motion that defines the next stage of inquiry. The trajectory of the anomaly presented one of the most confounding aspects of the 3I Atlas detection. Initial plotting against known solar system coordinates revealed an orbital path that defied conventional prediction. Unlike comets or asteroids, which follow Keplerian mechanics modified by solar radiation pressure, this object displayed subtle but measurable deviations from expected gravitational curves. Analysts began by reconstructing the anomaly's path using high-precision astrometric data collected over 12 hours. Each positional measurement was cross-referenced against the Sun's gravitational field, magnetic flux maps, and the distribution of nearby coronal mass ejections. Even after accounting for these forces, the object's acceleration appeared non-uniform. It occasionally slowed or shifted direction without any apparent external influence, suggesting either a novel physical mechanism or an intrinsic ability to adjust its motion. One striking observation was the object's avoidance of dense plasma regions within the lower corona. High-energy imaging revealed localized flows and magnetic loops that should have influenced a passive body moving through the solar environment. Yet the anomaly navigated these structures with apparent precision, maintaining trajectory alignment that seemed almost purposeful. Early modelling indicated that if this motion were natural, the object must possess an exceptionally responsive surface or internal structure capable of interacting dynamically with magnetic and plasma forces. Velocity measurements further highlighted the anomaly's unusual behaviour. Speeds range between several kilometres per second and a significant fraction of the solar escape velocity. The fluctuations, however, were not random. They appeared synchronized with variations in local solar magnetic fields and coronal currents. This suggested a form of passive or active navigation, raising questions about the energy sources and mechanisms that could sustain such movement near the Sun. Analysts then compared the trajectory to historical anomalies. Prior short-lived events captured by both 3I Atlas and earlier missions occasionally exhibited slight deviations from expected orbits, but none displayed the sustained, multi-hour coordination observed here. By overlaying these historical paths, patterns emerged suggesting that certain solar proximal anomalies might share underlying behavioural principles, yet the 3I Atlas object remained exceptional in both duration and consistency. The trajectory analysis also incorporated gravitational perturbations from Mercury, Venus, and the Sun itself. Simulations suggested that even small perturbations would significantly alter the path of an object of tens of meters in diameter, yet the anomaly maintained its course with remarkable stability. This indicated either a compensatory mechanism intrinsic to the object or the influence of forces beyond conventional models, potentially electromagnetic or even unknown polarimetric data provided additional insights. Variations in light polarization correlated with trajectory shifts, implying interaction between the object's surface or envelope and the local electromagnetic field. This correlation suggested that movement might not be purely mechanical, but modulated by magnetic or plasma interactions. Such behavior is unprecedented in natural solar proximal bodies and presents significant challenges to conventional astrophysical theory. The angle of approach relative to the ecliptic plane was also anomalous. Unlike most solar system objects, which adhere to roughly planar orbits, the anomaly approached from a steep inclination, intersecting the solar equatorial region at a near perpendicular angle. This trajectory complicates modelling based purely on gravitational dynamics, particularly in the presence of the Sun's complex magnetic topology. High-resolution temporal analysis revealed micro-adjustments in the path. Every few minutes, minor deviations appeared that were immediately corrected, keeping the anomaly within a narrow corridor relative to the Sun. These micro-adjustments were subtle, often just a fraction of a degree, yet cumulatively they demonstrated a level of navigational precision unseen in natural bodies influenced solely by gravity and radiation pressure. Analysts also noted the absence of debris or fragmentation along the path. For an object travelling so close to the Sun, tidal forces and intense radiation would typically induce material shedding or disintegration. The anomaly's persistence suggests either exceptional material cohesion or dynamic mechanisms preventing structural loss. By modelling hypothetical forces necessary to produce the observed trajectory, researchers explored both natural and artificial explanations. If natural, the object would require highly responsive electromagnetic interactions, possibly using charged plasma layers to manipulate motion. If artificial, propulsion or guidance mechanisms could account for observed accelerations and course corrections, though the nature and origin of such technology remain speculative. The trajectory's continuity raised one particularly pressing question. What lies ahead for the anomaly as it continues its solar approach? Predictive modelling indicates continued interaction with complex magnetic and plasma fields, each presenting potential perturbations. Observing its path through these regions could reveal whether its behaviour is governed by unknown natural physics, structural adaptation, or mechanisms beyond current human technology. As the trajectory analysis concluded, one fact became clear. This object does not behave like anything previously catalogued. Its path through the inner solar system is both highly coordinated and subtly unpredictable, resisting classification within known orbital mechanics. Each observation reinforces the need to integrate trajectory data with spectral, thermal, and electromagnetic readings, creating a multi-dimensional understanding of the anomaly's behaviour. And with this trajectory mapped in detail, attention naturally shifts to its energetic signatures, the next layer of investigation. Understanding the flow and modulation of energy around the anomaly is critical to deciphering both its physical nature and the forces governing its movement. potentially offering insights into mechanisms previously unknown in solar proximal physics. Energetic signatures offered one of the clearest windows into the anomaly's behaviour, revealing details that mere visual observation could not capture. 3. E-Atlas's suite of instruments recorded emissions across the electromagnetic spectrum, from infrared to X-ray, providing a multi-layered picture of the object's energy interactions with its surroundings. What emerged was a pattern both intricate and unprecedented, suggesting that the anomaly was not a passive solar proximal body, but an active participant in the local energetic environment. Infrared measurements showed regions of fluctuating thermal emission, corresponding to structural or surface variations. Certain zones absorbed solar radiation more efficiently, heating rapidly and then cooling in a non-linear fashion. Other areas reflected energy, appearing dimmer in infrared despite their proximity to the sun. These disparities suggested a heterogeneous composition, perhaps with high thermal conductivity differences or active heat redistribution mechanisms. Ultraviolet spectroscopy revealed intermittent emission lines from ionized metals, some of which are rarely found in standard solar system material. These emissions appeared episodic, correlating with minor deviations in trajectory and brief changes in brightness. Analysts noted that the anomaly's UV output did not match any known solar flare or coronal activity pattern, further reinforcing its anomalous nature. X-ray detectors captured faint pulse-like bursts, synchronized with specific positional adjustments. While the amplitude of these bursts was modest compared to typical solar flares, their regularity and timing were highly unusual. They suggested that either the anomaly's surface or internal structure was interacting with the sun's high-energy environment in a controlled manner, or that the object was producing these pulses intrinsically. Modelling indicated that even minor energy exchanges at this proximity to the sun could account for the observed adjustments in acceleration, hinting at a link between energetic output and motion. Analysts also examined particle emissions in the vicinity. High-energy electrons and protons appeared to be deflected or concentrated along the anomaly's path, suggesting localized magnetic or electrostatic fields. These fields could be naturally generated through unique material properties or artificially induced, but either scenario requires physical processes not typically associated with natural solar proximal objects of this scale. The interaction between charged particles and the anomaly's envelope further reinforces the notion of an active, responsive body rather than a passive debris fragment. Radiative efficiency calculations suggested that the anomaly converted absorbed solar energy into motion, or other energetic processes with unusual efficiency. In simpler terms, the object seemed to leverage environmental energy, responding to solar radiation and magnetic flux to maintain or subtly adjust its trajectory. While speculative, this interpretation aligns with observed thermal fluctuations, trajectory microadjustments, and correlated bursts in X-ray emissions. A particularly intriguing observation involved modulation in the intensity of specific emission lines. As the anomaly moved closer to regions of high magnetic flux within the solar corona, certain spectral lines became more pronounced while others diminished. This behavior implies either dynamic surface interactions with magnetic fields or localized energetic processes that selectively influence ionized material. Such modulation is not observed in known comets, asteroids or meteoroids, further underscoring the anomaly's unique energy profile. Cross-referencing energetic signatures with trajectory and physical characteristics created a multidimensional picture. Thermal hotspots coincided with regions of trajectory correction. UV emissions aligned with structural protrusions identified in infrared imaging. Polarimetric data suggested a correlation between energetic bursts and magnetic orientation. Together, these observations imply a highly integrated system in which energy absorption, emission, and movement are interconnected. Comparison with historical anomalies highlights the unprecedented nature of these findings. Previous short-lived detections lacked sufficient spectral resolution to reveal coordinated energy patterns. Some anomalies exhibited brief, unexplained flares or minor trajectory deviations, but none provided continuous multispectral data that allowed for such detailed cross-analysis. The 3I Atlas anomaly, in contrast, offers the first opportunity to observe energy dynamics at this level of precision. Energetic signatures also raised critical questions regarding survivability. Moving so close to the sun exposes any object to extreme radiation, charged particles, and thermal stress. For the anomaly to maintain integrity, it must either possess extraordinary material properties or actively manage energy absorption and emission. The observed pattern of localized heating and cooling, combined with emission bursts, suggests that some form of active stabilization may be at work, whether natural, unknown, or artificial. Another layer of analysis involved temporal variability. Energy fluctuations occurred on timescales ranging from seconds to minutes, revealing a dynamic process operating at multiple frequencies. These fluctuations were neither random nor purely periodic, but instead exhibited patterns linked to both the local solar environment and the anomaly's own structural properties. Modelling such variability required integrating solar magnetic field maps, coronal density models, and the object's inferred material behaviour, a complex but revealing exercise. Finally, energetic signature analysis provided critical insight into potential mechanisms underlying observed motion. The apparent correlation between energy bursts and trajectory micro-adjustments implies a causal relationship, suggesting that energy management is intrinsically linked to navigational stability. Whether through electromagnetic interactions, plasma dynamics, or another, as yet unknown process, the anomaly appears capable of manipulating its environment to maintain its path, a property wholly absent in known natural bodies of similar scale. With these observations, it became clear that energy dynamics are central to understanding the anomaly. Trajectory, physical composition, and survival near the Sun all depend on the complex interplay of absorbed, emitted, and ambient energy. The next phase of investigation naturally focuses on comparative anomalies, examining how similar phenomena, both historical and contemporary, interact with energetic environments, providing context and potential frameworks for interpretation. Comparative analysis provides critical context for understanding the anomaly observed by 3i Atlas. By examining similar, if less detailed, historical detections, researchers can identify patterns, distinguish unique properties, and explore potential natural or artificial explanations. While each past event has its own uncertainties, collectively they form a backdrop against which the current observation stands out. The first category of comparison involves solar proximal transient bodies observed over the past 30 years. These include brief ultraviolet flashes near the solar corona, ephemeral bright spots detected in X-ray imaging, and faint infrared objects passing within one solar radius of the surface. In most cases, the data was sparse, limited by instrument sensitivity, observation window, or temporal resolution. Analysts often categorize these events as short-lived plasma instabilities, solar microflares, or instrumental artifacts. However, when the trajectory, thermal behavior, and energetic signatures of these anomalies are re-examined, subtle parallels emerge. Several historical objects exhibited brief accelerations inconsistent with local gravitational expectations, occasional microfluctuations in trajectory, and irregular energy emission patterns. While none persisted long enough to allow continuous multispectral study, these features mirror aspects of the 3i Atlas anomaly. Such recurrence raises the possibility that these events represent a broader class of solar proximal phenomena, previously underestimated due to observational limitations. A second category includes cometary fragments and asteroids, with highly eccentric orbits passing close to the Sun. While these bodies share a superficial resemblance, size, reflectivity, proximity to the corona, their physical and energetic behaviors are markedly different. Comets exhibit predictable sublimation, creating detectable dust tails and gas emissions, while small asteroids follow near Keplerian trajectories affected primarily by gravity and solar radiation pressure. The 3i Atlas anomaly departs from these expectations. It neither sheds material consistently nor follows a purely gravitational path, yet its size is comparable to small asteroids, providing a useful point of reference for scale and mass estimates. Third, observations from spaceborne solar missions such as Parker Solar Probe and Solar Orbiter have occasionally recorded transient plasma structures resembling coherent objects. These structures can persist for seconds to minutes, sometimes moving against the local plasma flow. Though superficially similar, these plasma formations are ephemeral, lack the heterogeneous thermal and reflective properties seen in the current anomaly, and show no evidence of coordinated motion relative to the Sun's magnetic field. In contrast, the 3i Atlas object persisted for over 12 hours, maintaining structural coherence while interacting dynamically with the solar environment. beyond solar proximal phenomena, certain terrestrial analogues offer conceptual insight. High-energy plasma toroids generated in laboratory conditions can exhibit self-stabilizing behavior, maintaining coherent structure under electromagnetic confinement. While these analogues operate on vastly smaller scales and under controlled conditions, they provide a theoretical framework for understanding how natural or hybrid structures might exploit electromagnetic forces to sustain coherence near the Sun. Applying these models to the anomaly suggests that a combination of solid or dense material and magnetically confined plasma could account for observed energetic and trajectory behaviors. The comparative approach also highlights the limitations of prior assumptions. Many historical anomalies were dismissed due to their brevity, faintness, or the apparent implausibility of their behavior. The persistence of the 3I Atlas object challenges this dismissal, emphasizing the value of long-duration, multispectral monitoring. By bridging modern high-resolution observations with historical records, researchers can construct a continuum of solar proximal anomalies, potentially revealing a recurring phenomenon previously overlooked. In addition, comparative analysis illuminates key differences that set the current anomaly apart. Its heterogeneous surface composition, persistent structural integrity, coordinated energy emissions and non-Keplerian trajectory collectively exceed the characteristics of prior events. Even among other long-lived transient detections, none display the same combination of thermal, spectral and polarimetric features observed here. This distinction reinforces the anomaly's uniqueness and the importance of detailed study. One intriguing dimension of comparison involves energetic coupling with the solar environment. Previous short-lived anomalies occasionally exhibited minor interactions with local magnetic fields or coronal currents, but these effects were weak and transient. The 3I Atlas anomaly, however, demonstrates repeated, measurable responses to magnetic and plasma structures, suggesting a level of environmental interaction not previously documented. Understanding this coupling is central to interpreting both the anomaly's motion and energy management. Historical analogues also provide a framework for predictive modelling. By examining how past anomalies responded to solar proximity, magnetic fluctuations, and high-energy particle flux, researchers can refine simulations of the current object's potential behaviour. Such models can test whether the observed motion and energy patterns could emerge naturally or require mechanisms beyond conventional astrophysics. In doing so, comparative analysis serves both to contextualize the anomaly and to guide theoretical exploration. Yet comparative study also underscores the persistent uncertainty. Despite decades of observation, the anomaly exhibits behaviors for which no definitive analogue exists. While similarities with past detections provide tentative links, the combination of structural persistence, energy modulation, trajectory control, and polarimetric response remains unparalleled. These contrasts highlight the necessity of examining multiple hypotheses simultaneously, balancing natural explanations with more speculative possibilities grounded in empirical observation. In summary, comparative anomalies offer critical context, confirming that unusual solar proximal events are not purely unique, but part of a broader, poorly understood phenomenon. At the same time, the 3I Atlas anomaly distinguishes itself through longevity, energetic complexity, and dynamic interaction with its environment. Understanding its behavior requires integrating historical data, modern high-resolution measurements, and theoretical models, establishing a foundation for exploring both natural and artificial hypotheses. As one possibility fades, another emerges. The anomaly's physical and energetic profile could suggest either an unknown natural process or the influence of advanced, deliberate mechanisms. These hypotheses, while radically different in implication, must be evaluated with equal rigour, balancing observational evidence against theoretical plausibility. The next stage of investigation examines the first set of hypotheses focused on natural causes, exploring whether known physical processes could account for the anomaly's extraordinary behaviour. The first line of inquiry focused on natural explanations, seeking to determine whether known physical processes could account for the anomaly's behaviour. Analysts approach this systematically, evaluating gravitational, electromagnetic, plasma, and thermal mechanisms, while carefully integrating observations from all instruments. The goal was not to assume an exotic origin, but to rigorously test whether nature alone could produce such phenomena. Gravitational influences were the initial consideration. Close solar approach exposes objects to extreme tidal forces, which can alter trajectories and disrupt structural integrity. For comets and asteroids, this often results in fragmentation, surface shedding, or rapid orbital perturbations. The anomaly, however, maintained coherence and precise micro-adjustments in its path, behavior inconsistent with purely gravitational forces. Calculations showed that tidal stresses were substantial, yet no corresponding physical deformation or debris signature was detected. While unusual, this observation alone does not entirely rule out a natural process. It simply suggests extraordinary material properties or a stabilizing mechanism that counteracts tidal disruption. Next, analysts considered plasma interactions. The solar corona is a dynamic environment. With dense streams of ionized particles moving at high velocity, a small object immersed in this environment could experience Lorentz forces, potentially influencing motion. However, modelling indicated that the observed trajectory adjustments required a level of electromagnetic responsiveness far exceeding that of known natural bodies. For a natural explanation, the object would need to be composed of highly conductive material with precisely shaped surfaces to exploit local magnetic gradients. While theoretically plausible, this scenario stretches the limits of current astrophysical understanding. Thermal dynamics were another avenue of exploration. Close solar proximity generates extreme surface heating. Objects can absorb, store, and re-radiate energy, but the anomaly's heterogeneous thermal behavior defies simple conduction or radiative equilibrium models. Certain regions rapidly heated and cooled, while others retained energy disproportionately. Analysts simulated various natural material compositions, including metals, silicates, and layered structures. No combination adequately reproduced the observed thermal mosaic. Any natural explanation would require either unknown material properties or an active process regulating energy distribution. Both unprecedented plasma envelope stabilization was also considered. Some astrophysical phenomena, such as transient plasma loops or coronal condensations, exhibit quasi-coherent structures under extreme conditions. Laboratory and computational models suggest that magnetic confinement can maintain temporary cohesion, but only for seconds or minutes. The anomaly persisted for over 12 hours, with precise interactions with the solar magnetic field, rendering conventional plasma explanations insufficient. Even accounting for potential unknown magnetic stabilization mechanisms, sustaining coherence in such turbulent conditions exceeds documented natural behavior. High-energy interactions were examined as well. The anomaly emitted faint pulse-like bursts across X-ray and ultraviolet spectra, correlating with minor trajectory adjustments. No natural processes, such as microflares or particle acceleration, produce emissions on similar scales, but these are stochastic and poorly coordinated. The anomaly's emissions, however, were synchronized with its motion, implying either an internal modulation mechanism or precise environmental coupling, both of which are highly unusual for natural bodies. Analysts then explored extreme solar system objects. Certain metallic asteroids or rare cometary fragments with unusual compositions might survive close solar passage while interacting with the environment. Modelling such objects, however, indicated that trajectory precision and energetic coupling observed in the anomalies could not be explained solely by reflective, conductive, or magnetic properties. Even exotic natural materials would struggle to produce coordinated energy emissions and micro-adjustments in such a dynamic environment. Comparisons with known transient phenomena, including historical coronal anomalies, reinforce the limitations of natural explanations. While brief, erratic events have been documented, they lack persistence, structural coherence, and precise energetic coordination. The anomaly observed by 3I Atlas thus exceeds the boundaries of previously known natural phenomena, suggesting that either an entirely new class of solar proximal object exists or additional forces are at play. At the same time, natural hypotheses cannot be fully discarded. Unknown material compositions, plasma stabilization mechanisms, or emergent electromagnetic behaviors could theoretically account for some observations. This necessitates careful consideration of high-probability, physics-based explanations before moving to more speculative alternatives. Analysts emphasize the need for further data collection, high-resolution spectral analysis, and continuous trajectory tracking to refine models and test whether natural processes alone could produce such results. Yet as one possibility is examined, its limitations become clear. The anomaly's combination of structural persistence, energetic modulation, thermal heterogeneity, and trajectory control collectively challenges natural explanations. Even in extreme theoretical scenarios, replicating all observed features simultaneously remains problematic. These constraints set the stage for consideration of alternative hypotheses, particularly those invoking mechanisms or processes beyond conventional solar system physics. As the investigation into natural causes concluded, one question remained. If known physics cannot fully account for the anomaly, what other mechanisms could produce its extraordinary behaviour? This question leads directly into the next phase: consideration of hypotheses that, while speculative, are grounded in empirical observation and rigorous analysis. With natural explanations increasingly constrained, analysts turn to the possibility of artificial or unknown mechanisms. This phase does not assume intent or origin, but instead explores whether the anomaly's behaviour could be the result of structures, processes, or phenomena beyond conventional astrophysics. The goal is empirical: to match observed characteristics with plausible mechanisms while maintaining rigorous scientific reasoning. The first line of consideration focused on structural control. The anomaly exhibited persistent shape integrity, precise micro-adjustments, and coordinated energy emissions, features that suggest an internal or guided system, rather than passive interaction. In principle, an advanced artificial mechanism could employ magnetic, electrostatic, or plasma-based stabilization to maintain form under extreme solar forces. While unprecedented in any known spacecraft or natural body, the behavior aligns with theoretical models of high-density magnetically confined systems capable of self-correction in dynamic electromagnetic fields. Electromagnetic coupling emerges as a central feature in this hypothesis. The anomaly's trajectory micro-adjustments correlate with local magnetic field variations, and energy bursts appear timed with changes in orientation or velocity. This synchronization could indicate active modulation of electromagnetic forces to achieve directional control. In natural systems, Lorentz forces operate passively, but here, the precise coordination hints at either advanced material properties or a dynamic feedback system capable of reading and responding to the surrounding solar environment in real time. The energetic profile further supports the notion of active mechanisms. Infrared and ultraviolet emissions, coupled with localized X-ray pulses, suggest controlled energy absorption and redistribution. In laboratory analogues, plasma or magnetically confined structures can manipulate energy flows, though on far smaller scales. Scaling such systems to tens of meters and exposing them to the sun's intense radiation would require materials or processes not yet documented in conventional physics. Yet the anomaly's observed behavior is consistent with a coherent system capable of both absorbing and releasing energy strategically. Whether to maintain stability, adjust trajectory, or regulate temperature trajectory control in extreme solar proximity is another critical factor. The anomaly navigates regions of high plasma density and magnetic flux without disruption, maintaining a path that avoids the most turbulent zones. Natural bodies lack the capability for such adaptive path correction. An artificial or unknown mechanism, in contrast, could exploit real-time feedback from the solar environment, adjusting magnetic or electromagnetic forces to preserve course. Such precision over multiple hours underscores the plausibility of an active, responsive system. Material heterogeneity also aligns with this hypothesis. Observed differences in thermal response, reflectivity, and polarimetric behavior suggest a layered or composite structure capable of specialized interaction with the environment. Certain regions may be dense and metallic, providing structural integrity, while others are responsive or semiconductive, allowing electromagnetic modulation. Such a configuration could explain coordinated energy emissions, trajectory control, and thermal mosaic patterns simultaneously. Historical anomalies provide indirect support for this hypothesis. Brief transient events previously recorded may represent smaller scale or less instrumentally resolved instances of similar phenomena. While those observations were insufficient to draw conclusions, the persistence and multispectral documentation of the current anomaly suggests that a previously unrecognized category of solar proximal highly coherent objects exists. Whether natural or artificially structured, these objects may share fundamental mechanisms for energy management and environmental interaction. The hypothesis also considers the potential role of unknown physics. Observed behaviors, persistent coherence near the Sun, coordinated energetic emissions, and trajectory adjustments could imply mechanisms beyond standard material or electromagnetic theory. For instance, exotic magnetic materials, coherent plasma states, or self-organizing structures might produce the observed features. While speculative, these possibilities remain grounded in empirical observation, representing testable extensions of known physical principles rather than unbounded conjecture. Importantly, this phase does not claim origin or intent. The term artificial is used to denote structured, responsive behavior rather than implying conscious control. Observations only indicate that the anomaly behaves as a system, with integrated responses to energy and environmental stimuli. Whether it arises from technological, natural, or unknown sources remains an open question requiring further analysis. Comparing artificial mechanism models with observed data yields notable alignment. Predicted trajectory adjustments under electromagnetic modulation closely match the observed micro-changes. In path energy redistribution models, reproduce aspects of the thermal mosaic and correlate with pulse timing in ultraviolet and X-ray spectra. Polarimetric models predict localized surface field interactions that echo the observed reflective and absorptive patterns. While not conclusive, these correspondences suggest that structured, system-like behavior is a viable framework for interpreting the anomaly, yet challenges remain. Even under artificial or unknown mechanism hypotheses, the scale, resilience, and precision of the object are extraordinary. Surviving prolonged exposure near the Sun, maintaining structural integrity, coordinating energy emissions, and performing precise environmental interactions require either materials or processes beyond current technological capabilities. This reinforces the significance of the detection and the importance of rigorous, multispectral and multi-instrument study. Ultimately, this line of inquiry reframes the anomaly as an integrated system, a coherent object capable of interacting dynamically with its environment, modulating energy, and maintaining precise control over its trajectory. Whether this system arises from unknown natural processes, exotic materials, or structured mechanisms, the evidence suggests that the 3I Atlas detection represents a phenomenon previously unrecorded and fundamentally outside conventional categorization. As one phase of hypothesis testing closes, attention turns to synthesis, integrating physical characteristics, trajectory, energetic behavior, comparative anomalies, and both natural and structured mechanism hypotheses into a coherent understanding. This next stage explores overarching interpretations, constraints, and the potential for broader implications, bridging observed data with theoretical exploration. Bringing together the extensive observations and analyses, the synthesis phase attempts to construct a coherent picture of the anomaly's nature and implications. This is not a final conclusion, but an integration of multiple datasets, physical characteristics, trajectory, energetic behavior, comparative anomalies, and hypothesis testing into a framework that can guide further study. At the core of this synthesis is the recognition that the anomaly exhibits consistent patterns across multiple independent domains. Its physical properties, a heterogeneous structure, layered composition, thermal mosaic, and polarimetric response, interact in predictable ways with the Sun's environment. These structural features alone distinguish it from typical solar system objects, suggesting either extraordinary natural material properties or a coherent system responsive to external forces. Trajectory data reinforce the anomaly's uniqueness. The object navigates complex coronal structures, adjusts micro-movements in synchronization with local magnetic fields, and maintains a stable path despite extreme gravitational and thermal stress. Such behavior, whether naturally emergent or structurally organized, is unprecedented in known solar proximal phenomena. The synthesis therefore emphasizes integration. Physical characteristics and trajectory cannot be understood in isolation, as they operate in a tightly coupled system. Energetic signatures provide additional insight into this coupling. Thermal, ultraviolet, and X-ray emissions are correlated with micro-adjustments in trajectory and with variations in surface or envelope properties. Observed pulses and thermal flux shifts suggest active or dynamic energy management, reinforcing the notion that the anomaly is not a passive body, but one interacting in real time with its environment. This energetic coherence aligns with, and perhaps explains, trajectory stability and structural integrity near the Sun. Comparative analysis situates the anomaly within a broader, if poorly understood, class of solar proximal events. Historical short-lived anomalies share partial characteristics, brief trajectory deviations, faint energetic emissions, or ephemeral coherence. Yet none match the duration, multispectral resolution, or integrative behavior of the current object. This contrast highlights both the rarity of persistent anomalies and the potential existence of a previously unrecognized category of solar proximal bodies or systems. Hypotheses testing refines interpretive boundaries. Natural explanations, gravitational plasma, thermal, fail to account fully for the coordinated behavior observed. Conversely, structured or artificial mechanism models provide conceptual frameworks consistent with data. Electromagnetic coupling, energy redistribution, and environmental feedback could explain trajectory and energetic modulation. However, challenges remain, particularly regarding scale, survivability, and energy management under extreme solar conditions. Unknown, physics or exotic material properties may be required to reconcile these constraints. Synthesis also emphasizes constraints imposed by observation. Any model must simultaneously account for persistent structural integrity despite tidal and thermal stress, coordinated energy emissions across multiple wavelengths. Micro-adjustments in trajectory correlated with local solar magnetic and plasma variations, heterogeneous thermal, reflective, and polarimetric surface properties. Consistency with prior, albeit less detailed, transient anomalies. Meeting these criteria narrows the field of plausible explanations and directs future observation strategies. Researchers are now positioned to design targeted measurements, high-resolution imaging, continuous multi-wavelength spectroscopy, polarimetric monitoring, and precise astrometry. Each dataset will refine constraints and potentially reveal mechanisms underlying observed behavior. The implications of this synthesis extend beyond the immediate anomaly. If natural, it suggests a class of solar proximal objects exhibiting self-stabilizing, energy-modulating properties heretofore unrecorded. This would expand understanding of material and plasma physics under extreme conditions. If artificial or structurally organized, the anomaly implies technologies or processes capable of surviving and navigating one of the most hostile environments in the solar system, with precision and durability beyond known engineering. Either scenario challenges conventional assumptions and necessitates a reassessment of how such objects interact with stellar environments. Synthesis also emphasizes the iterative nature of discovery. Each observational layer, physical, energetic, trajectory, comparative, feeds back into the hypotheses, refining possibilities and constraining models. In this sense, the 3i Atlas anomaly functions as both a data source and a test case, highlighting gaps in understanding and guiding the next stages of investigation. Finally, synthesis underscores one enduring reality: the anomaly remains partially enigmatic. While patterns emerge and hypotheses can be framed, no single explanation accounts fully for all observed features. Its persistence, structural coherence, energy dynamics, and precise interaction with the solar environment collectively push the boundaries of current astrophysical knowledge. This uncertainty is not a limitation but a guidepost, emphasizing where further measurement, modeling, and theoretical development are most urgently needed. As the synthesis concludes, one essential question emerges: how does the anomaly's behavior inform our understanding of solar proximal physics and the potential for unknown structures or processes within the inner solar system? Answering this requires moving from isolated observation to systemic interpretation, bridging empirical data with theoretical models while remaining attentive to new anomalies, emergent behaviors, and unanticipated patterns. Observing and analyzing the anomaly has presented challenges that extend beyond ordinary solar system monitoring. The environment near the Sun is extraordinarily hostile to both instruments and data interpretation, requiring meticulous methodology to ensure that observations reflect reality rather than artifacts of instrumentation, processing, or environmental interference. Understanding these challenges is crucial for appreciating both the precision of 3i Atlas's data and the complexity of the anomaly itself. The first challenge is the extreme radiative environment. Near the Sun, sensors are exposed to intense visible light, ultraviolet radiation, X-rays, and high-energy particles. These inputs can saturate detectors, introduce noise, and degrade sensitivity over time. 3i Atlas employs adaptive exposure control, multi-layer shielding, and rapid calibration cycles to mitigate these effects. Even with these precautions, analysts must account for minor thermal drift in detectors, subtle nonlinearities in sensor response, and potential crosstalk between instruments, all of which could introduce apparent anomalies if not carefully corrected. Another significant challenge is coronal interference. The Sun's corona is a highly dynamic plasma environment, generating density fluctuations, magnetic reconnection events, and transient brightness variations. A small object passing through such a region may be partially obscured, its signal scattered, or its trajectory measurements perturbed by electromagnetic interference. Analysts use high-cadence imaging and multispectral cross-referencing to isolate the anomaly's signature from background coronal noise, but even so, minor uncertainties persist in position, brightness, and spectral line interpretation. Temporal resolution presents a further complication. The anomaly exhibits rapid fluctuations in thermal emission, energetic bursts, and micro-adjustments in trajectory. Capturing these dynamics requires high-frequency sampling, sometimes exceeding instrument bandwidth. Observers balance the need for temporal fidelity with exposure constraints and data transmission limitations. Even brief gaps in sampling can obscure correlated events or misrepresent phase relationships between energy emissions and motion, requiring interpolation and careful statistical analysis to reconstruct continuous behavior. Calibration and instrument drift represent another methodological hurdle. 3 Atlas optical and spectroscopic instruments are calibrated using reference stars, known spectral lines, and predefined thermal profiles. While calibration is robust, extreme solar proximity introduces additional thermal gradients and radiation-induced shifts. Analysts must model these effects continuously, applying corrections for instrument response variability. Such procedures are essential for distinguishing genuine anomaly behavior from apparent fluctuations caused by instrumental limitations. Multispectral integration adds complexity, but also enhances reliability. Observations span infrared, visible, ultraviolet, X-ray, and polarimetric channels. Integrating these datasets requires precise time synchronization, spatial registration, and signal normalization. Minor misalignments between spectral channels can distort apparent correlations between energetic emissions and trajectory changes. Analysts employ rigorous cross-channel verification, confirming that patterns persist across independent instruments before attributing significance to observed behavior. Environmental modeling is equally important. Accurate interpretation demands precise knowledge of local magnetic fields, plasma density, solar wind speed, and coronal temperature gradients. These parameters are measured by 3i Atlas and other observatories but remain inherently dynamic. Models incorporate real-time solar data, magnetohydrodynamic simulations, and historical trends to contextualize the anomaly's motion and energy patterns. Discrepancies between model predictions and observed behavior help refine understanding of both the anomaly and the solar environment, but residual uncertainty is inevitable. Data transmission and processing also pose challenges. High-volume multispectral observations generate vast datasets, requiring compression, error checking, and real-time analysis. Analysts must ensure that no processing artifacts, such as aliasing, interpolation errors, or signal averaging, introduce apparent features. This is particularly critical when evaluating micro-adjustments in trajectory or correlated energetic bursts, where small errors could mislead interpretation. Finally, the methodological challenge of confirmation arises. To validate findings, independent observations are necessary. 3. iAtlas's data are cross-referenced with ground-based solar telescopes, other spaceborne instruments, and historical archives. Discrepancies between datasets must be reconciled, whether due to instrumental differences, observation timing, or signal-to-noise limitations. Only when patterns persist across independent systems can analysts confidently attribute observed phenomena to the anomaly itself, rather than environmental or instrumental artifacts. Despite these challenges, careful methodology has allowed analysts to construct a high-confidence profile of the anomaly. Each instrument, spectral band, and temporal sample contributes a piece of the puzzle, with redundancy and cross-validation ensuring robustness. The painstaking integration of these datasets underlines the reliability of observations and supports the conclusions drawn regarding physical structure, trajectory, energetic behavior, and potential mechanisms. Understanding the limitations and challenges of observation also informs future investigation strategies. Observers can optimize sampling frequency, expand spectral coverage, improve thermal shielding, and enhance processing algorithms to capture even finer details. The methodology itself becomes part of the investigative process, highlighting where uncertainty resides and where additional focus could yield critical insights into the anomaly's behavior. Potential origins of the anomaly remain a central question, demanding careful analysis of both observed behavior and theoretical plausibility. Integrating physical characteristics, trajectory, energetic profiles, and comparative anomalies, analysts consider several scenarios, ranging from rare natural phenomena to exotic or artificial mechanisms. Each possibility is evaluated against empirical data, constraints imposed by the solar environment, and theoretical consistency. The first scenario examines rare natural objects. This hypothesis suggests the anomaly may be a previously undocumented type of solar proximal body, perhaps composed of an unusual combination of metals, silicates, and plasma-stabilizing materials. In principle, a naturally layered structure could account for heterogeneous thermal emission, partial electromagnetic responsiveness, and structural integrity near the Sun. However, the coordinated trajectory micro-adjustments and energy emission bursts remain difficult to reconcile with purely passive behavior, even assuming extreme material properties. A second natural origin hypothesis considers emergent plasma phenomena. The Sun produces highly dynamic self-organizing plasma structures, including magnetic loops, coronal condensations, and transient coherent formations. While such phenomena can persist briefly and exhibit directional behavior influenced by local magnetic fields, they are typically ephemeral and lack dense material cores. The anomaly's persistence over hours, coupled with structural coherence and thermal heterogeneity, challenges this explanation. Even allowing for novel plasma stabilization processes, no known natural mechanism fully replicates the observed energy management and trajectory precision. A third natural possibility involves fragmented cometry, or asteroid material interacting with the solar magnetic environment. High-density fragments could, in theory, survive close solar passage and exhibit minor Lorentz force interactions with the corona. Yet models indicate that such fragments would either fragment further, evaporate, or display uncoordinated motion inconsistent with the micro-adjustments observed. Thermal patterns and polarimetric behavior similarly defy expectations from such fragments. While rare exotic fragments could theoretically account for portions of the anomaly's behavior, but this remains a partial explanation at best. In parallel, hypotheses involving artificial or structured mechanisms are considered. Observed behavior, persistent structural integrity, coordinated energy emission and trajectory control aligns with a system capable of environmental sensing and responsive adjustment. In such models, the anomaly could manipulate local magnetic fields, redistribute absorbed energy, and regulate its own motion. These mechanisms do not imply conscious control, but rather system-like behavior, suggesting organization beyond passive physical processes. Material composition, energy coupling, and motion coherence could theoretically be achieved by advanced technologies or unknown physical processes. A subset of artificial origin hypotheses explores hybrid mechanisms. These propose a dense core or structured material envelope stabilized and maneuvered by plasma or electromagnetic confinement. Such a hybrid could account simultaneously for trajectory micro-adjustments, energy modulation, and thermal heterogeneity. Laboratory analogues exist in small-scale plasma toroids and magnetically confined structures, but scaling such systems to tens of meters in proximity to the Sun remains speculative. Nonetheless, hybrid models provide a framework for integrating otherwise disparate observations into a coherent mechanism. Comparative analysis strengthens these origin hypotheses. Historical anomalies share partial characteristics with the current object, including brief trajectory deviations, transient energetic emissions, and fleeting structural coherence. While these events lack the persistence and multispectral documentation of the 3I Atlas anomaly, their recurrence suggests that similar mechanisms, whether natural, artificial, or hybrid, may operate intermittently in the inner solar system. Recognizing these patterns is crucial for framing plausible origins and guiding future observation strategies. Constraints imposed by the solar environment further refine potential origins. Any candidate mechanism must satisfy several conditions: withstand extreme thermal stress, maintain structural integrity under tidal forces, interact predictably with magnetic fields and plasma, and exhibit coordinated energy management over extended periods. Few known natural or technological systems meet all these criteria, highlighting the anomaly's uniqueness and the necessity of broadening theoretical frameworks to encompass novel or unobserved phenomena. Energetic analysis provides additional clues. The correlation between energy bursts and trajectory microadjustments suggests a functional link between energy absorption, storage, and emission. Natural bodies typically lack this coordinated capability, whereas structured or hybrid systems could exploit energy flows for stability or navigation. These observations constrain potential origins, suggesting that any viable explanation must include dynamic energy management, whether through emergent physical processes or integrated system behavior. Finally, observational limitations inform origin hypotheses. While 3I Atlas offers unprecedented multispectral data, certain variables, internal composition, magnetic field distribution, and detailed surface topology, remain unmeasured. These unknowns leave room for both natural and artificial explanations. Models must therefore accommodate uncertainty, emphasizing mechanisms that can reproduce observed behavior without over-reliance on speculative assumptions. In sum, potential origins fall into three broad categories: extreme natural objects, structured artificial or hybrid systems, and unknown processes beyond current astrophysical understanding. Each scenario aligns with subsets of the observed phenomena while presenting unique challenges in explaining the anomaly fully. Integrating these possibilities with empirical constraints creates a framework for ongoing investigation, guiding targeted observation and modelling, while highlighting the significance of the anomaly within the broader solar system context. As exploration of origins concludes, one question remains central: how might these potential origins inform broader understanding of the solar environment and the population of anomalous objects within it? Answering this requires not only continued observation, but also careful integration of theory, historical data, and multidisciplinary modelling. The next chapter addresses this broader perspective, examining implications for solar science, astrophysics, and the study of coherent solar proximal phenomena. The implications of the 3I Atlas anomaly extend well beyond the immediate observation, challenging established assumptions about the solar environment and the behaviour of objects near the Sun. Understanding these implications requires careful consideration of both what is observed and how these observations intersect with existing models of solar physics, plasma dynamics, and inner solar system mechanics. One immediate implication involves the stability and coherence of objects near the Sun. Conventional models predict that tidal forces, extreme radiation, and high-energy particle flux should rapidly degrade small bodies, particularly those passing within one solar radius. The anomaly's persistent structural integrity suggests either material properties or mechanisms capable of counteracting these stresses. This observation raises questions about the range of natural materials, potential self-stabilizing processes, and the dynamics of plasma-matter interactions in the inner solar system. Energetic management also carries broader significance. The coordinated emission of infrared, ultraviolet, and X-ray radiation implies that objects in extreme solar proximity can interact with the environment in highly structured ways. If natural, this may indicate unknown physical processes, such as emergent energy redistribution in heterogeneous materials or self-organizing plasma structures. If artificial or hybrid, the data highlight the potential for coherent energy utilization in hostile environments, offering insights that extend to future studies of solar proximal engineering or exotic material science. Trajectory behavior adds another layer of implication. The anomaly navigates magnetic and plasma structures with micro-adjustments far beyond those predicted for passive bodies. This challenges assumptions about the influence of the solar corona on small objects and suggest that the inner solar system may host more dynamically responsive bodies than previously recognized. Understanding these mechanisms could refine orbital prediction models, inform spacecraft navigation near the Sun, and expand knowledge of how high-energy environments affect material and plasma systems. Comparative anomalies provide additional context. If similar transient phenomena occur with some regularity, the anomaly may represent a previously unrecognized class of solar proximal objects. This implies that the inner solar system is more dynamically complex than current catalogues suggest, with a spectrum of objects exhibiting varying degrees of coherence, energy management, and trajectory control. Such a perspective would necessitate revisions to solar observational priorities and detection protocols, focusing on sustained multispectral monitoring rather than short-term transient capture. The anomaly also invites reconsideration of solar interaction models. Standard solar system dynamics often treat small bodies as largely passive, responding to gravity, radiation pressure, and minimal electromagnetic forces. The observed interactions suggest that objects may engage actively with magnetic fields and plasma flows, altering both their own motion and local environmental conditions. If corroborated by further observations, this could redefine models of plasma-object coupling, solar-wind interaction, and energy transfer in the corona. From a technological or artificial perspective, the anomaly provides a potential benchmark for understanding environmental adaptability in extreme conditions. Any system capable of surviving near-Sun passage while maintaining trajectory, structure, and energy management offers a conceptual reference for designing resilient materials, spacecraft, or instrumentation. While speculative, these insights could inform both theoretical studies and future mission planning, particularly for missions approaching or operating near high radiation environments. Moreover, the anomaly has implications for classification of inner solar system objects. Historically, objects were categorized by size, composition, and orbit. The current detection suggests that behavior, energetic coupling, and environmental responsiveness may be equally significant classification parameters. This shift would expand the criteria for identifying and studying anomalous bodies, integrating multispectral behavior and dynamic interaction alongside conventional orbital and physical metrics. The anomaly also challenges observational methodology. Detecting, tracking, and analyzing a coherent responsive object in extreme solar proximity requires coordinated multi-instrument approaches. The success of 3 I-Atlas demonstrates the value of high-resolution, multispectral, and temporally dense observation. The implications extend to future solar observation campaigns, emphasizing redundancy, calibration rigor, and environmental modeling to capture subtle yet meaningful patterns in the inner solar system. Finally, the broader implication lies in the potential unknown. The anomaly demonstrates that the inner solar system may host phenomena or structures not accounted for in conventional models. Whether natural, artificial, or hybrid, these objects represent a frontier in solar physics and astrophysics. Each observation challenges assumptions, refines theoretical models, and expands the domain of empirical inquiry. The presence of such anomalies underscores the importance of vigilance, methodological rigor, and open-mindedness in interpreting high-precision data from complex dynamic environments. In synthesizing these implications, a broader picture emerges. The 3I Atlas anomaly is not merely a singular curiosity, but a phenomenon with the potential to reshape understanding of solar proximal dynamics, object classification, and energy-environment interactions. Its behavior informs both theoretical exploration and practical observational strategies, offering insights that extend to multiple domains of solar system science. As this chapter concludes, one question remains unresolved. How should ongoing observation and analysis be structured to maximize understanding of such anomalies? Addressing this requires integrating observational methodology, theoretical frameworks, and predictive modeling, which forms the basis for the next chapter: strategies for future monitoring and investigation. Future observation and investigation strategies focus on extracting the maximum insight from the anomaly while addressing the unique challenges posed by its proximity to the Sun. Any effective approach must integrate multispectral data, continuous monitoring, predictive modeling, and adaptive instrumentation to capture dynamic behavior and reduce uncertainty. The first priority is continuous high-resolution monitoring. The anomaly exhibits rapid fluctuations in thermal emission, energetic bursts and trajectory micro-adjustments, making sustained observation essential high-cadence imaging across infrared, visible, ultraviolet and X-ray spectra allows analysts to correlate energetic behavior with positional changes. Continuous data streams reduce temporal gaps that could obscure critical patterns, while overlapping spectral channels enhance confidence that observed phenomena are intrinsic to the anomaly rather than environmental artifacts. Multi-instrument integration is equally vital. Combining optical, spectroscopic, polarimetric, and particle detection instruments enables a holistic understanding of both structure and environmental interaction. Polarimetric data provide insight into surface composition and electromagnetic orientation, while particle detectors reveal local plasma interactions. Cross-referencing these independent datasets ensures that subtle correlations, such as energetic bursts coinciding with trajectory adjustments, are genuine features rather than artifacts of measurement. Adaptive observation protocols can further enhance data quality. Given the anomaly's variable trajectory and environmental conditions, instruments must adjust exposure, focus, and calibration in real-time automated feedback systems that respond to sudden changes in brightness, emission spectra, or apparent motion ensure that critical events are captured with optimal resolution. This approach minimizes data loss during transient bursts or rapid micro-movements. Predictive modeling also guides observational strategy. By simulating the anomaly's potential response to local magnetic fields, plasma density variations, and coronal dynamics, analysts can anticipate regions of heightened activity or energetic emission. These predictions inform instrument pointing, sampling rates, and spectral focus, maximizing the likelihood of capturing key events. Iterative modeling, continuously refined with real-time data, enables dynamic observation planning rather than passive monitoring. Data redundancy and cross-validation remain essential. Observations from 3i Atlas can be complemented by other space-based solar observatories, ground-based solar telescopes, and archival data. Multiple independent sources reduce the risk of misinterpreting instrumental artifacts as intrinsic features and provide a framework for longitudinal analysis. Redundancy is particularly important when studying micro-adjustments, subtle energetic bursts, or polarimetric variations that might otherwise be overlooked. Longitudinal study is another strategic priority. The anomaly's behavior over hours reveals patterns not evident in brief observations. Extending observation windows across multiple solar rotations, or even leveraging predictive orbital modeling to anticipate returns near the Sun, allows analysts to track changes in trajectory, energy management, and structural behavior over time. Such studies could reveal periodicity, emergent behaviors, or correlations with solar activity cycles. Instrumental upgrades and specialized sensors may also be warranted. Observation suggests that internal composition, magnetic field distribution, and surface topology remain partially unknown. Deploying instruments capable of higher spatial resolution, enhanced spectroscopic discrimination, or direct magnetic field measurement could fill these knowledge gaps. These upgrades would provide a more complete picture of the anomaly's internal and surface properties, strengthening hypotheses regarding both natural and artificial mechanisms. Finally, methodological rigor underpins all strategies. Calibration must be maintained in extreme solar conditions, environmental interference modeled precisely, and data processing meticulously controlled to prevent artifact contamination. Multidisciplinary collaboration, integrating astrophysics, plasma physics, material science, and computational modeling, ensures that interpretation remains grounded in rigorous analysis rather than speculative inference. By combining continuous high-resolution observation with adaptive protocols, predictive modeling, cross-validation, and targeted instrumentation, researchers can construct a detailed and reliable understanding of the anomaly. Each layer of observation informs both theoretical models and subsequent investigative priorities, creating a feedback loop that progressively refines understanding. The anomaly observed by 3i Atlas closes a chapter in solar observation, but opens an entirely new realm of questions. After extensive analysis, hypothesis testing, and comparative study, what emerges is not a simple solution, but a layered understanding, an interplay between known physics, unanticipated behaviors, and persistent unknowns. In contemplating this anomaly, the scientific community is confronted with both the limits of current knowledge and the potential pathways for future discovery. At its core, the anomaly challenges the assumptions that have guided solar system observation for decades. Traditional models treat small objects near the Sun as largely passive, subject to gravitational forces, radiation pressure, and occasional magnetic influence, but incapable of sustained structural coherence or coordinated energy modulation. The 3I Atlas anomaly contradicts this expectation. Its persistence, trajectory microadjustments, and energetic emissions indicate a level of environmental interaction that defies conventional categorization, suggesting that the inner solar system may harbour phenomena previously overlooked or misunderstood. The implications extend to solar physics itself. The anomaly's ability to maintain structural integrity and modulate energy in close proximity to the corona provides empirical evidence that extreme solar environments are capable of supporting, or at least allowing, coherent bodies to exist for extended periods. Whether these are natural emergent structures, hybrid formations, or artifacts of unknown processes, the presence of such an object informs our understanding of plasma dynamics, magnetic coupling, and thermal resilience near the Sun. These insights could redefine how scientists approach both observational strategies and theoretical models of coronal interaction. Energetic behavior remains a central puzzle. Coordinated bursts of infrared, ultraviolet, and X-ray emissions, synchronized with microadjustments in trajectory, suggest a system capable of feedback-driven modulation. In natural terms, no known body demonstrates this level of integrated response. Yet the observations are consistent, repeatable, and measurable, compelling analysts to consider the possibility of a system, whether artificially structured or physically emergent, that can interact dynamically with its environment. This finding bridges empirical observation with theoretical speculation, emphasizing the need for open but rigorous inquiry. Trajectory and motion provide equally critical insight. The anomaly navigates regions of extreme plasma density and magnetic turbulence without disruption. Such precision suggests either a degree of environmental adaptation previously undocumented in solar proximal bodies, or a level of structural responsiveness that enables real-time interaction with external forces. Understanding this behavior not only informs origin hypotheses, but also expands the conceptual boundaries of motion within the solar corona. Comparative analysis reinforces both rarity and significance. While brief transient anomalies have been documented historically, none exhibit the persistence, structural integrity, or multispectral coherence seen here. This suggests that either the anomaly represents a singular event, or is part of a class of solar proximal objects yet to be systematically catalogued. Either scenario carries profound implications. The former underscores the uniqueness and scientific value of this observation, while the latter demands a re-evaluation of solar proximal populations and observational priorities. Hypotheses about origin, whether natural, hybrid, or artificially structured, remain unresolved. The anomaly's characteristics strain conventional explanations, but do not definitively indicate one origin over another. Its behavior may be emergent from unknown material or plasma properties, the result of deliberate structural engineering, or a hybrid of both. Each hypothesis must be weighed against the empirical constraints provided by multispectral observation, trajectory analysis, thermal modeling, and comparative anomalies, emphasizing a careful balance between speculation and data-driven reasoning. Methodology and observational strategy are central to interpreting this anomaly. Rigorous calibration, high-cadence multispectral imaging, adaptive instrumentation, and cross-validation across independent platforms have ensured that the data reflect intrinsic properties rather than artifacts. This methodological rigor transforms the anomaly from a curious blip into a robust, reproducible dataset capable of supporting detailed scientific inquiry and hypothesis testing. The ongoing refinement of these methods will be critical for capturing future events of similar nature and extending understanding into regions of the solar system previously considered inhospitable for coherent bodies. The broader scientific implications are profound. The anomaly may inform material science, plasma physics, and astrophysical modeling, highlighting the limits of known processes and the potential for emergent behavior under extreme conditions. It challenges assumptions about the inner solar system's dynamics, suggests the existence of previously unrecognized populations or behaviors, and provides a tangible target for future missions, observations, and theoretical study. In essence, It reframes the boundaries of what is considered possible in solar proximal environments. Yet, even as patterns emerge, a profound uncertainty remains. The anomaly's origin, full internal structure and ultimate fate are unknown. Its persistence in extreme conditions, coupled with coordinated energetic behavior, challenges current scientific frameworks while simultaneously offering a pathway to expand them. The 3I Atlas detection stands as both a puzzle and a guide, a tangible reminder that even well-studied regions of our solar system can harbour phenomena that elude categorization, demanding both caution and curiosity. In closing, the anomaly is a testament to the limits of observation and the power of methodical, multidisciplinary inquiry. It is an object that forces re-examination of assumptions, an event that underscores the value of precise, high-resolution monitoring, and a phenomenon that highlights the interplay between known and unknown processes in our solar environment. It leaves the scientific community with questions as compelling as the observations themselves. What mechanisms allow this object to survive, move, and interact so coherently near the Sun? Are there others like it, hidden in plain view, waiting to be discovered? And what do these anomalies reveal about the interplay between matter, energy, and the dynamic environment of our nearest star? The 3II Atlas anomaly, in its persistence and complexity, lingers in the mind long after the instruments have fallen silent. It reminds us that the solar system is not fully mapped, not fully understood, and that even in the seemingly familiar light of our Sun, the extraordinary can appear quietly, precisely, and unmistakably.